Welcome, everyone. My name is April Smith. I'm the Education Coordinator at NAFA. Welcome to the Sustainable Fleet Technology webinar series, Electric Vehicle Battery Reuse and Recycling. Before I turn things over to our presenters for today's session, there are a few housekeeping notes to review. This session is being recorded, and a copy of that recording will be made available on the NAFA website in the coming week. All participants are muted during the presentation to limit background noise, but we do encourage you to ask questions and add comments using the chat and Q&A features. You can find these on the Zoom toolbar. If you do experience any technical difficulties, you can reach out to the NAFA team through the chat feature. And now to kick things off, it's my pleasure to turn things over to Heather Brutz.
Hello, everyone. My name is Heather Brutz. I am the Transportation Program Director for the North Carolina Clean Energy Technology Center. And we have been doing this, the Sustainable Fleet Technology webinar series for a number of years now. And in recent years have been doing it as a partnership with NAFA. And so very pleased to have all of you here today. The topic of today's webinar is electric vehicle battery reuse and recycling. I get a lot of questions from this, which was one of the reasons why I thought it was worthwhile to go and do a webinar. So I did also want to go and announce about some upcoming, first would like to go and thank our sponsors, the United Soybean Board, Lakey Services, Pioneer eBoost, and Geotab. So we do have some upcoming webinars that I wanted to make sure that you were aware of. November 6th, November 20th, and December 4th. The November 6th webinar will be on signal prioritization in transit and emergency vehicles. The November 20th webinar is going to be on key performance indicators, and the December 4th webinar is going to be on off-road electric equipment. We'd love to see you on those webinars. You can go to the link or to the QR code showing, and you can register there. So I am now going to turn this over to Ted Spencer, who is going to be today's moderator. Ted Spencer is the climate policy analyst for Common Defense. He's also a former coworker of mine, so very pleased to be working with him again. So Ted is a Navy veteran. He served in the Navy for 9 years. Both his bachelor's in electrical engineering and his master's in public administration are from North Carolina State University, where I work and where we used to work together. And he's also worked as a consultant in the electrical engineering industry, and now is a climate policy analyst at Common Defense. So I'm going to hand it over to Ted Spencer.
Thank you so much, and thank you everybody for joining us. Heather, great working with you again. It's had a lot of great times working together for 5 years at the Clean Tech Center. It's great to be back working in this arena. So my interest in this is because we are looking at the recycling portion of it, the energy, the materials, as well as the possibility for future career and workforce development in these arenas. So just want to do brief introductions of our speakers today. Albert Lipson is working at Argonne National Laboratory. David Giacob is working at Scoutit, and Stephen Mearsman is at Zenobē, and they will be covering various different arenas around this issue and offering their perspectives, their knowledge, and the work that they're doing in these arenas. So without further ado, I'll turn it over to Albert Lipson for the beginning of the presentation.
All right, thank you very much for the introduction. Take a minute to get those slides up.
Yeah. Okay, are you seeing the correct slides right now?
Yep. So today my part of this webinar is really to talk about the recycling processes. I'm particularly going to be talking about lithium-ion batteries, which are the most likely ones that are going to be in electric vehicles. So if you can go to the next slide. So given the diverse audience and the like, I thought it might be useful to start kind of at the very most basic level. So what really is a lithium-ion battery? What does it contain? So you may be familiar with lithium-ion batteries. They're in your cell phone, power tools, obviously electric vehicles, basically anything that's plug-in hybrid or greater uses a lithium-ion battery these days, and actually most hybrids as well. So really the components of a lithium ion battery are relatively straightforward. So you have an anode. This is also, you can call it the negative electrode. That's graphite. In today's cells, there are some cells that have silicon these days, but pretty much everything's graphite. Then you have a positive electrode. So this is some sort of cathode material. There's a lot of different varieties, but this is the one that contains the nickel, manganese, cobalt. It could also be lithium iron phosphate, a lot of different options. Then you have a plastic separator in between these two electrodes to prevent them from touching and shorting out the battery. And then you have a liquid electrolyte that goes around this. I'm gonna say what the liquid electrolyte is, but I don't expect anyone to remember. It's lithium hexafluorophosphate and a combination of ethylene carbonate and other carbonate solvents. Essentially, it's a fluorinated, relatively toxic and flammable electrolyte. This liquid that goes in between. It's not really liquid in the battery, it's absorbed into everything. So if you just cut open a cell, it's not going to leak out like a lead acid battery would, but it certainly is there. So if you go to the next slide. So I want to put this slide up because it kind of gives an idea of where we are on recycling right now. So this was done a few years ago. We probably should update this analysis. But nonetheless, essentially, this is, what it looks like when you delay the recycling of batteries by 10 years from when they're basically put into service and using the projections of when electric vehicles will come into service. What you kind of gather is we start really reaching large volumes for recycling kind of in the neighborhood of 2030. And from there, it really grows exponentially. Essentially, this is when, this big wave of new electric vehicles that are coming on the market now are starting to reach end of life going forward. The real issue with recycling in a lot of ways is, there's a lot of demand for minerals that goes into these batteries. And so recycling can really resolve some of these material demands that we have to be able to produce the batteries in the first place. So if we can get those materials back, it can be really helpful. Go to the next slide. So one thing I want to highlight is that, so people do recycling of lithium ion batteries today. Depending on the battery, it may actually be profitable for the recycler at their plant, but it's not always the case. The processes they're using right now are reaching relative maturity. There's a lot of different processes. I'll kind of go into a few more details into what those processes really look like and some future options. Most of the processes now, though, really what they're trying to get back is the metals themselves. And so they basically just recoup the metals value. This doesn't work for all the chemistries, which I'll go into a little bit more detail later. The other issue with this is the profitability of recycling is relying on the metals price. So if the metals price drops, suddenly the recyclers can't make money anymore. So that can be a big issue going forward. Go ahead and go to the next slide. All right, so what recycling actually looks like today. So essentially, they're starting with shredding the batteries, and they get out what's called the black mass. Essentially, they beat the daylights out of the battery until all the powders, which are the actual electrode materials, come off. They're current collectors, and then they collect that, and then they can then put that into a separate process for separating out the metals. There's right now two main categories of processes. So hydrometallurgical, which is essentially putting that material into acid and you leach out all the metals from that, and then you separate all the metals in liquid form. and then get them back that way. The other option is you can smelt everything back into an alloy of metals, and then you can separate the alloy of metals back in, which usually actually requires hydrometallurgical processing in the end anyway. So really pyro is kind of a pre-treatment for hydro processing. Go to the next slide. So this happens to be the mission statement for the center I work for, but I really think it's actually the mission for all of recycling. So really the goal here is, can we decrease the cost of recycling enough so that we actually get these materials back that are important? So that's the lithium, nickel, cobalt, primarily that is of interest. And then, of course, we'd like to reduce the cost of actually making those materials. So that's the environmental costs of digging the stuff out of the ground, the energy that goes into that, as well as the chemicals and environmental waste that go into that to produce the raw materials. Go to the next slide. So here's kind of a chart that sort of gives you a better idea of how these processes all fit together. So I already talked about the hydrometallurgical process, the raindrop type, the pyro process, smelting stuff back in. So what you can see is they have relatively big loops. So essentially, if you do pyro, you have to go back through the refining steps and re-refine out your metals. If you go through the hydro loop, you have to go back through the cathode manufacturing process, and that's actually a relatively expensive process. It also has a lot of waste associated with it and a lot of energy. And then the pyro process also has to go back through that cathode manufacturing process. And this works well for some materials, but less than others. So these are just some of the common cathode materials here in the top right. So LCO is lithium cobalt oxide. That's what's in your phones and computers. It has a huge metals price because cobalt's expensive. So you can get a lot of money back basically by getting the metals out. NMC, this is a common cathode material in electric vehicles. That's nickel, manganese, cobalt. It's actually lithium, nickel, manganese, cobalt oxide. So that has a decent amount of metals value. But you can see you're losing still a lot of value from the cathode production. But if you go to the other two types, so you have lithium manganese oxide and lithium iron phosphate, particularly the lithium iron phosphate basically has no metals value. So if you ever want to actually have a profitable recycling process, recycling lithium iron phosphate, then you really have to do something different. And that's really the motivation for why we work a lot on what we call direct recycling. So direct recycling is an approach to basically get the cathode material back as the cathode material, so you don't dissolve it back in elements where you have to remanufacture into cathode production. So I'm just reading the comments, sorry. So in any case, that's kind of where we're at in recycling terms these days. Direct recycling is up and coming. It's a future process we're working on now. So if you go to the next slide. So I just kind of wanted to give you an idea of what the recycling looks like in a little more detail. So this is what a recycling process looks like for direct recycling. Although the processes are sort of somewhat similar for the other types, just these later steps are a bit different. So you start, so all the processing starts with some sort of shredding. You're going to take the battery and you're going to basically use some sort of shredding mechanism to get it down to smaller sizes. So that's that first part. Likely while you do that, you're going to do something with the electrolyte. Typically, they put these things in water, and essentially the electrolyte goes into the water, and then you have to deal with the water later. From there, you're doing some sort of separation process to basically get out the metals. So these are the current collectors that the electrodes are actually coated on. So that's copper and aluminum, as well as the casing materials. There's some other components that come out in the metals fraction. You could want to get out the plastics so they're not in your way. That's the separator, that plastic piece, as well as some of the casing components, maybe plastic. And then you get out the cathode and anode. For direct recycling, you also have to be able to separate the cathode material from the anode material. And we have various ways of doing that by magnetic separation or froth flotation. Different techniques that are relatively straightforward to separate those materials. Then you have to get rid of the other components that are there. So there's also carbon black and a binder, which is polyvinylidene difluoride, or PVDF. It has fluorine in it, which makes this kind of a pain to get rid of. It's hard to resolubilize. And then for direct recycling, you do relithiation, because that's one of the main degradation mechanisms, and it goes back into the battery manufacturing. So that's the kind of general process. For the others, essentially you're getting out the metals, salts instead at the end. But otherwise, the kind of general picture is the same. Of you take the battery, you shred it, you separate it, you then get out the components you're interested in. So if you go to the next slide. So I wanted to show you some pictures of batteries being shredded because, one, I think they're fun to look at. The second reason is to kind of explain a couple little details about batteries. So if you are shredding batteries, one, you have to do so very carefully. So this is actually an inerted atmosphere shredder. Often industrially, they use water sprays or the like to contain any flames or that kind of thing. This particular battery is what would be one cell in an electric vehicle. It weighs a couple of pounds going through the shredder. It's fully discharged. And the reason you can tell that is it doesn't actually produce very much heat when it goes through the shredder. This looks very different when you actually start charging the battery. If you go to the next slide. So this is a few cells at different states of charge. Hopefully the video doesn't freeze too much. But you can see there's a huge difference between even moderate states of charge, 30% charge, 50%, compared to 100%. So really this kind of is one as a safety message that if you're ever doing bad things with batteries, don't have them fully charged. That's one lesson. The other one is this is an inner atmosphere shredder, and yet it still catches on fire. And I'll explain that in the next slide really quickly here. Go to the next slide. So this is kind of probably overly technical for this audience, but I just thought I'd mention that essentially what happens is when you have the material that doesn't have enough lithium in it, you basically decompose that material into something that produces oxygen. So now you have oxygen, you have a flammable electrolyte, and while it's doing this decomposition, it also produces a whole bunch of heat. So now you have everything you need basically to create a fire inside the battery. And essentially you have an explosive because you have an oxidizer, you have a fuel, and you have heat to ignite the whole thing. So it can be quite violent, the reaction, depending on the exact conditions. But this is really one of the main reasons why lithium-ion batteries catch on fire and why they're so hard to put out. Go to the next slide. So I just kind of wanted to mention some overall safety things with lithium-ion battery packs, especially if any of you are interested in ever dismantling these or handling them more often. So one of the things is if you are dismantling a pack, you should be aware that these have a lot of voltage on them. Packs can be up to 800 volts these days. And then also, if you accidentally short these batteries, you can get currents in the thousands of amps. So essentially that means you have an arc flash hazard. So you can get a basically burst of energy from the battery that creates a molten plasma of metals that can shoot out at you. So that's not great. You can have this thermal runaway process that's basically caused by this cathode decomposition process that I talked about, where it keeps heating up and will light itself on fire. if you accidentally short the battery. Another thing, batteries are very heavy. So a lot of the packs in a lot of these vehicles are 1,000 pounds, roughly speaking. So you have to be pretty careful not to drop them on people. Um, so one thing, if you're storing a lot of batteries, you need to have good handling practices. And something, plan basically when the batteries catch on fire. When I talk to our recycling partners, they say that it's kind of inevitable. So you really do need to have some options and thought process into what you actually will do. It's a good idea to thermally monitor your batteries. That can tell you if there's something that's happening and give you some time to actually get the battery, let's say, outside, so it doesn't burn down your plant or your storage location. The other things, the battery electrolyte is flammable and toxic. So one doesn't want to play around with it very much. It does produce hydrofluoric acid, which is really quite nasty if you know anything about that. The cathode material is not great either. It's a carcinogen. It'll cause cancer. And then more for the recycler side, I have this note in about if you have other battery types mixed into your feedstock, you can also have other issues with those materials. If you go to the next slide. So I just kind of wanted to quickly show you what separation actually looks like. So this uses the process that we developed here at Argonne for doing direct recycling. So you can basically see we can go from this shredded mess into individual piles of materials. And it actually works pretty well. So this is what people are actually doing, is essentially doing this kind of processing. The current process is a little more mixed. So you get the mixed cathode anode, the mixed metals, and then the separator is a separate piece. You go to the next slide. Just kind of a quick note. So what recyclers are actually recycling these days is not a lot of end-of-life batteries. So the recyclers are actually focused on manufacturing scrap these days because that's the main source of material. So this is a slightly different process. It happens to work better for direct recycling, but in any case, it's actually what a lot of the recyclers are relying on right now. If you go to the next slide, it kind of shows you how this all plays out over time, where in the next 5 to 10 years, essentially, or longer, the scrap will dominate the overall picture of lithium-ion battery recycling from the manufacturers. And then those end-of-life batteries that are coming from the vehicles that you might have really don't start kicking in until much later. So last few little things, I just wanted to talk about some modeling work we've done. So if you go to the next slide. We have a model that basically evaluates how recycling occurs. This includes some transportation components and the like going in, as well as the entire recycling processes. And we can essentially compare all the different recycling processes against each other. This uses a lot of different models that Argonne had previously made. One's called GREET, the other one's called BATPAC for doing this analysis. Go to the next slide, I can show you some of the results for that. Basically to show you that recycling is actually a good thing environmentally, and I think actually probably by cost as well in most cases. I'll note that you can see pyro is a little bit above the cost of virgin production in this particular model, but if you actually go to larger scales, the pyro process actually gets a little more cost efficient. So you actually can make money doing that as well. But overall, the environmental impacts, basically everything's better. If we eventually can go to this direct recycling process, it's really the ideal. But there's a lot of challenges involved in actually doing direct recycling overall. So one more slide, and then I will leave it to our next speaker. So one thing that came up actually in our pre-meetings about this is a question of whether electric vehicles are really better than gas vehicles. I'm just showing you the greenhouse gas emissions. So this is essentially looking at what a gasoline vehicle would be versus different types of electric vehicles. Probably the most common type of electric vehicle these days is going to be this BEV 300, meaning 300-mile range. When you look at this, essentially, you get about half the per mile CO2 emissions that you do in a gas vehicle. So really, and this is looking at the entire process from manufacturing all the way through end of life for the batteries. You can look up this report if you want to read more details. And then it gets even better if you go towards wind and solar for electricity. Essentially, if your electricity grid doesn't produce CO2, then you're only having the CO2 from production, and that's about 10% of what a gas vehicle would be. So with that, just leave it on the acknowledgement slide for a second. Next slide. So just want to say that the center I work for has a lot of people in it, a lot of different institutions, and we're certainly here to talk about things. If you're ever interested in hearing more about something, or if you have a question, feel free to reach out. So thank you very much for your time.
Albert, thank you so much. Really appreciate all the information. Great seeing those videos too. It's always fun to see things blowing up, if you ask me.
I agree. I love watching it, blow up. So.
And we'll be getting into the questions again at the end, just as a reminder of seeing some questions that have already been coming in and some comments there as well. Next up, we'll have David Giacob, who is the co-founder and CEO of Scouted, to speak specifically about recycling environment.
All right. So good afternoon, everyone. My name is Davide Giacobbe, and I'm the CEO and co-founder of Scouted. So a little bit about me. My background is a mechanical engineer with over a decade of experience in automotive industry. I began my career at Yamaha Motor as a vehicle engineer, and following that, I spent 7 years at Automobili Lamborghini as a team leader, again in the engineering department, where I brought several models from concept to series production, focusing on delivering, integrating the electric technologies in the product range. And as the automotive industry shifted towards electrification over the past decade, I focus more and more on the challenges associated with electric vehicles, particularly on the end-of-life management of EV batteries and state of health, battery health determination. And that's what brought my co-founder and I to create Scouted in 2022. And at Scouted, we built a B2B marketplace dedicated to the repurposing and management of end-of-life EV batteries. And also we developed a technology to accurately determine the residual value and the health of electric vehicle batteries. That is a key factor to consider in the repurposing process, as I will explain later in this presentation. So we can go to the next slide. So today, I want to start by talking about EV battery repurposing. So what exactly is EV battery repurposing? Next slide, please. All right. So in simple terms, it's a process of taking batteries that are no longer suited for their original purpose, such as powering electric vehicles, and finding them what is called a second life in new applications. So you have to think about this circular economy approach, in which there are involved 3 main areas that we need to consider. So first one is the mobility sector, because you have to think in this process that these batteries in the repurposing process are flowing between the mobility sector to the renewable energy sector. So the mobility sector represents the source of these batteries. This includes automakers, or in general vehicle makers, auto recycling businesses, and battery disposal consortiums. So automakers are central in the EV battery repurposing process, because they play a crucial role in the collection and sorting of used batteries. And as Albert said before, most of the end-of-life EV batteries at the moment are coming from production scraps. So a lot of production plants are nowadays the sources of these second life batteries. Then there are auto recycling businesses. such as auto dismantlers or auto dismantling businesses. And they usually handle the physical retrieval and sometimes the initial processing of these batteries. And then there are disposal consortium that ensure that these batteries are managed responsibly at the end of their life cycle. Most of the times sometimes are non-profit associations, especially in the European countries, in which they are taking care of collection and correct disposal for like nationwide. Then the second area we need to consider is the battery and energy storage industry. I will expand on this topic later in this presentation, but this sector is the one that receives the battery from the mobility sector and focuses on transforming these used batteries into viable energy storage solutions. They refurbish and integrate batteries into systems that can store energy for various applications. And last area we need to consider and focus on is the renewable energy sector. So this is the sector that uses the battery storage applications made with Second Life batteries for basically three main, that we can break down in three main categories. So residential, commercial or industrial, and grid scale. And residential are basically power walls that can power like homes and small applications. Commercial and industrial means that businesses are utilizing energy storage to reduce and manage their energy costs and provide backup power. And grid scale, we are talking about large scale energy storage solutions that support the electrical grid by balancing supply and demand, integrating renewable energy sources, and in general, improving grid stability. So we can go now on the next slide. So let's expand a bit on battery storage to let you better understand what we're talking about. Battery storage systems are in general systems that store electrical energy for later use using the chemical energy stored in batteries. And battery energy storage systems are one of the most common uses for repurposed EV batteries. So these systems store energy generated from renewable sources such as solar or wind that are intermittent. And having an effective storage system in place ensures that energy captured from renewables can be used when needed, even when sun or wind are not allowing for the power to be generated. And on top of that, battery storage systems can respond almost instantaneously to fluctuations in demand or generation of power, injecting or absorbing power to stabilize the grid frequency. And this is particularly important, and I would say necessary, to maintain the quality of power being delivered and grid reliability, especially as renewable energy sources become a larger share of the energy mix. Last point, very important, is that battery storage also helps lower greenhouse gases emissions because they are able to optimize the use of renewable energy sources. And when renewable energy, for example, is available, but demand is low, the excess energy can be stored instead of being wasted. So this stored energy can then replace the need for fossil fuel-based energy during periods of high demand or when renewable energy generation is insufficient. So about the, in general, last point is related to the market growth. Battery energy storage market is really growing fast and is projected to reach up to $160 billion by 2030. So it's a super interesting industry to follow. So next slide, please. Now that we have introduced battery storage, I want to talk about the advantages and benefits of battery repurposing. What can offer battery repurposing? So first of all, there is a point related to environmental impact and resource efficiency, because repurposing ensures that batteries are used to their fullest potential. and energy and materials invested in producing the battery deliver maximum utilities because we can extend their service life beyond initial applications like electric vehicles. And on top of that, extracting additional value from batteries will reduce the need for new raw materials such as lithium, nickel, and cobalt. And in general, we are reducing the environmental impact associated with mining and material processing. The second point is related to cost effectiveness and lower total cost of ownership because repurposing batteries reduce the overall costs associated with the battery life cycle. And using batteries for secondary application, we can make energy storage solution more economically viable. And in general, this is a target for the battery energy storage industry. There is as I said before, there is a high growth, high demand, and a lot of entities, especially in commercial industrial sector, are seeking for more economically and more affordable solution of energy storage. Third point is lower energy consumption and emission savings, because in general, we should always aim to repurpose a battery before recycling. As you have seen in the previous presentation, recycling is a very intense process and in terms of emissions, and extending the life of the batteries into recycling as a intermediate step. So at Scouted, we have demonstrated the potential of battery repurposing by creating a Second Life battery marketplace, an online platform that is designed to connect sellers and buyers in a way that they can maximize the value of these used electric vehicle batteries and supporting the growing demand for energy storage solutions. In general, the sellers on our platform are automakers or auto recycling businesses. And these businesses, as we said before, play a critical role in managing the end-of-life process for vehicles. And through the marketplace that we have created, they can resell batteries that are still valuable for second life applications, and they can lower the total cost of ownership and add an extra revenue stream supporting the circular economy process. On the other side, the buyers are companies in the battery energy storage sector that are seeking more affordable battery supply to build more affordable battery storage solutions. And these companies usually span across the three main categories that I talked about before. So residential, C&I, so commercial industrial, or grid scale. And in general, the most important, the fastest growing market segment in this, the fastest growing market categories in this segment is the C&I category. All right, we can go to the next slide. So we cannot talk about battery repurposing without mentioning that understanding battery health is crucial for several reasons. So why battery health is so important? Next slide, please. So first of all, we need to understand what is the remaining capacity. Knowing how much capacity is left in a battery helps determine its suitability for repurposing, because batteries with sufficient remaining capacity can be effectively used in second life applications, and we can ensure reliability and performance. Performance is a second key point, because detailed understanding of battery health allows us to predict how it will perform in its next use. So we can understand better what is the best application for these batteries. And this ensures also that the battery meets the specific requirements, whether it's for, again, residential, C&I, or grid support. Safety is another key point. Understanding state of health of the battery helps ensure that repurposed battery won't pose a risk such as overheating or like premature failure. And also proper assessment can prevent potential hazards, protecting users and all the equipment around those users. Last point, last but not least, is cost effectiveness. because correctly evaluating battery health up front, companies can avoid wasting time, resources on batteries that are not suitable for repurposing and that should be sent to recycling immediately. And this efficiency leads to cost saving and more effective allocation of resources, obviously. And in our case, to address these needs, we have developed Voltes, that is our last product, a unique tool capable of generating an accurate picture of the battery state of health in just a few minutes. It's particularly valuable to dealers in the EV industry or fleet operators and businesses that usually need to monitor battery health over time. We are also capable of collecting data periodically, and users can track performance trends, make informed decisions about their maintenance, but also repurposing and recycling down the line. Next slide. Okay, here I summarize the key factors for a successful battery repurposing. So first of all, we need collaborations across the value chain, because manufacturers, repurposers, regulators, but also recyclers must work together, especially on defining standard, but designing the process in a more efficient way in order to also generate more safety and cost efficiency for the entire process. Then we need accurate battery health assessment. As we discussed, understanding battery health is essential to determine suitability for second life applications and facilitate informed decision maker, enhance the reliability of repurposed batteries. Regulatory support is another key point, because supportive policies encourage sustainable battery management, and regulations can help also standardize practices, especially related to testing, ensuring safety, and also promoting investment in repurposing infrastructure and businesses. And the last point is the reason why I'm here today, because educating end users about the benefits of repurposed batteries is crucial. We need to increase awareness, driving demand, that could drive demand, support market growth, and also fostering acceptance of second life battery solutions. So in conclusion, EV battery repurposing present a really great and significant opportunity to advance full sustainability in both the automotive and energy sector. We are not only reducing environmental impact, but also unlocking great economical benefits, making energy storage more accessible and promoting the use of renewable energy sources. So I encourage each of you to consider how to might engage with this emerging field, even whether you are part of the automotive industry or energy sector, or simply interested in sustainable practices. Next slide. And yeah, thank you so much. Here are my contacts if you want to contact us and learn more about what we're doing in general about battery repurposing. Thank you.
And David, thank you so much. This is really interesting to me, thinking about, again, reusing these batteries and being able to take them and put them into different industries and different roles. We've seen some with stationary energy storage systems, so hopefully we'll see more of this in the future. And next we'll have Stephen Mearsman, who is with Zenobi.
Right. Shall I put the slides on? Just one second. Share. Oh, I can't share my screen. Can you share the slides? Ah, there we go. Can we full screen that somehow?
Would it be possible to give him the ability to share his slides directly?
Oh wait, I can do something now. Yeah.
I'll stop sharing.
All right, I am empowered. So hopefully you can see my screen now, and now it should even be full screen. So Stephen Mearsman, one of the founders and directors of Zenobi. Zenobi started as a developer, owner, and operator of grid scale batteries. So that's a bit what you see in the top left corner, these orange boxes. So imagine a 40-foot container sitting in a field, connected to the power grid and helping solve bottlenecks on the grid. So too much wind, that would overload the electrical grid and actually shut down the wind farm. So we're losing all this potential electricity. We try to solve that. Other issues could include stability issues because wind and sun, it can vary. So we need buffering on a sort of millisecond basis. So that's where we started. We've now got about 730 megawatts of that, which is the equivalent of a nuclear reactor. But what we quickly saw was that there's not just first mile problems on the grid, there's actually last mile problems on the grid as well, which is that if you put, say, 200 buses, which is typical depot size here in Europe, and you electrify them, that's the equivalent of 1.5 Empire State Buildings worth of electrical uh, load popping up in your backyard. So the grid's not always ready for that. So we started putting batteries in depots and eventually offering full charging infrastructure as a service. Now, the last thing we then noticed that was standing in the way of mass adoption to electrification is the cost. In many cases, electric vehicles cost more on day one. There may then be operational savings and fuel savings along the way, but that depends a bit on how much you drive and how long you drive the vehicle. So there's a gap there. The idea we had to close that gap was to repurpose the batteries from the vehicle in a second life. Because if they have more value in a second life, you can then come up with a pay-as-you-use structure for the vehicle in their first life, which takes into account that higher terminal value. Now, to pull that all together, we offer these services on a sort of a wrapped basis with a financing package. Now, what do we do with the batteries when they come off? You can see sort of from the icons here, we've used them on construction sites, music festivals, but also in CNI applications, as the colleagues before talked about, which in many cases is, say, taking somebody who's got a huge roof and put lots of solar on there, but then say they electrify their forklifts and charge them at night. How do you get the sun to shine at night? Well, you can't, so you need to shift it with a battery. So we operate in that whole ecosystem. We have the idea that the more we squeeze, as battery specialists, the more we squeeze value out of batteries in their first and their second life, the more cost-effective adoption of EVs will be. How do we do that? Well, we actually, and this is sort of slightly boring perhaps, but it's important to keep into mind how this leads to second life use, is that we actually say an electric vehicle consists of three bits. It's on one side getting it charged, right? The grid infrastructure is a really challenging thing. So how do you ensure the vehicles are charged on time at the lowest possible cost, with enough juice to last a full duty cycle? So we would engage all the way with the utility, build all the infrastructure all the way to the charging infrastructure, and then underwrite that for, I think the longest we've done is 18 years. And if we don't charge the vehicle, we pay for a replacement vehicle. The second bit is if you own a bus or a truck, you might run that again for 16, 18 years. In Australia, they even run it for 25. The battery's not going to last that long. It's going to degrade, so we need to replace it. Now, as an operator, you might say, well, what's a new battery going to cost? No one knows. When do I need to replace it? Depends on how you drive it. So we try to take that risk away by saying we guarantee a size of the fuel tank, so nobody will pay for the upfront battery and any battery replacements, and factor in the second life so that you pay a sort of a lower monthly fee, which means we're often quite competitive with sort of more traditional bank financing. Lastly, well, there's the rest of the vehicle, which is the chassis, the body, the metal, the glass, the seats. That's more of a typical, funding structure. We can add a lot of value there, like we do on the batteries. Second life being, I guess, slightly repetitive with my colleagues earlier, but if you look at it, the first life of a battery sort of starts on this chart in the bottom left corner at 100%. You use the battery, you get very little degradation, then a lot, and then eventually really a lot, and the battery might fail. Now, why do people take the batteries off the bus? They don't drive them into destruction. They drive them until they can no longer meet the range. It might be, say, for a school bus operation, 130 miles. In some transit applications, might be 250 miles. So actually, there's typically quite a bit of juice left in there. And the analogy we often use is the battery might not be good for running marathons anymore, but it can still run sprints in a second life application, which then adds a lot of value. And what you see on the right here is a portable generator. It looks a bit like a diesel generator, except it doesn't have diesel or reciprocating engines inside. It's got batteries. Now, the other bit, Second Life is great, but what's even better is delaying replacement. So by changing the way you charge, changing the way you drive, training your drivers to use more regenerative braking. We've even seen some people put thin film solar on their vehicles so that the dashboard and the 24-volt systems runs off that. The less energy you put through the battery, the longer it will last. So that's obviously the preferred scenario, because then, as you can see on the orange line here, you need less replacements than with the blue scenario where you need 2. And while there is value in a second life, the most valuable thing a battery can still do is be turned into kilometers or miles, depending on what part of the world you live in. I've sort of already talked about most of this bit, but recycling's great, but I think second life is even better because eventually these things will need to be recycled, right? But in many cases, recycling capacity or economics aren't fully there yet. And what I mean by that is recycling, if you look at it, we've been recycling lithium batteries for ages, right? From laptops, from phones, etc. But at the same time, not in these volumes. So the factories need to scale, and various other bits need to happen. Now, if we repurpose the batteries in a second life, we can delay the need for recycling and give the industry time to catch up with its capacity. And we can also keep the commodities within the country where the battery is being used, shortening supply chains with all the socioeconomic and potentially political benefits of that as well. Now, the other bit that's a bit challenging is if you look at the batteries that you see in the bottom right corner, if they're sitting in, it's a modular thing, right? You've got cells packed into modules, modules packed into packs, and you can sort of disassemble them, right? So if one of these elements is broken, you can still repurpose all the rest, which is great. However, in some cases, people might put this battery in a whole lot of resin and glue, and then it becomes a lot harder to disassemble. That's one challenge. The second challenge is data. You might drive your car in a very different way from the way I drive my car and the way the third person drives their car. And if you repurpose batteries, you're trying to string all these various batteries together. And like with any chain, that chain is as strong as the weakest link. So there's a lot of filtering and matching that needs to happen. And the more data you have from the first life, the better you can do that. Some applications, on-grid, off-grid. So on-grid, we've used it to boost grid capacity. So give an example, we're currently working on a bus depot in London near Heathrow Airport, where the utility called the customer and said, well, your grid connection is going to be delayed by 460 days. So we put a battery in there for that period that will boost their existing grid connection so they can at least run their vehicles to meet their obligations to their customer. Another example, upper right corner, is a music festival. We recently worked with Massive Attack and the UN to do a fully zero emission or nearly fully zero emission music festival where we power the main stage, the construction, the deconstruction, as well as provided temporary charging for vehicles and a pop-up bus depot so people could get from the train station to the festival without having to hop into a car or a diesel bus. Now, that's on grid. Off grid, there's also benefits. Everybody always says, well, why aren't you just doing pure battery? Why is there a diesel generator on this picture? Well, actually, because if you want to go fully off grid, then you need potentially quite a lot of batteries, which can get expensive. And in many cases, hybridizing your generator with your battery already offers a lot of advantages because diesel generators aren't very good at reacting quickly to changes in consumption. If you put a battery in between, which is almost like a digital technology, it can ramp up and down really quick. As a result of that, you can get a much smaller generator, so you save money. And secondly, the smaller generator will run less often, so less consumption. And thirdly, if it runs, it'll run at full load, which means it's running more efficiently. So in many of these cases, we've seen fuel savings of anywhere between 100 liters to 1,000 liters a day in some of these applications. And then thirdly, whether you're using solar, wind, or hydrogen, again, you need to match supply and demand. So having a battery in between there can really help that. We've done some projects in very remote locations like a temporary village in the Sahara Desert, an electric rally, and a television broadcast in a coal pit in Scotland, island power grids in Sicily and Sardinia, all powered by one or multiple Second Life EV bus batteries. The other benefit of doing this with Second Life is well, it's a natural application and it's a local supply chain and it's cost effective. But compared to First Life, a lot of these batteries have been graded for transport, which helps with their vibration resistance and dealing with movement, which is, if you try to do that with First Life batteries, the OEM in some cases may not even let you, or it'll affect the warranty. A case study here, Auckland Airport had put in some EV chargers, two to be precise. They had a nice orange brand, hence the pictures on the right. But the challenge that they had was that they needed to boost the grid supply to get an additional 40 kilowatts per charger. Now, people come and charge, they charge in short bursts, right? They might drink 25 kilowatt hours in half an hour and then they move on and drive away. And then a few minutes later, somebody else will arrive with their car. So actually, there's quite a lot of opportunities in between charging sessions to top up a battery and maximize the use of the existing grid connection and get more life out of it, rather than upgrading the grid connection, actually lowering the utilization of that connection. So what we actually enabled the charge point operator to do here is to double the income of the site and in parallel reduce their cost base, because in the evening peak, when people were coming to charge, rather than buy the very expensive electricity available, then they were actually taking some energy from the battery as well. So they earned back part of the fees they were paying us from the energy savings of having a battery on site. Now, what does that look like to make it nice and real? Is you're seeing lots of different colors on here, but this is power output for various bits of the setup. So you've got the input meter from the grid, an output meter, which is what the battery is doing, and then also what the conversion systems were doing. So you can sort of see whenever you go towards maxing out the grid connection around 40 kilowatts, the battery kicks in and provides the difference between what's requested and what's available from the grid connection. And whenever the grid connection wasn't being used, you suddenly see the battery going into the negative part of this chart, which means that it's charging up again in between the charging sessions. Now, that's a very practical application, hopefully interesting, and yeah, happy to answer any questions.
Great, thank you so much. So yeah, I think we will get into some of the questions here. So for any of the panelists, so first off, do we have any numbers about the percentage of mobile device batteries, laptops, cell phones, et cetera, that are currently being recycled?
Not my back, not my, I mean, maybe just, I don't have metric tons or units, but as far as I understand, about 98% is a statistic that people have always tossed at me is actually being recycled. The biggest issue with recycling laptops and phones is what they call the bottom of the drawer problem, which is that people actually don't hand them in to be recycled, but just keep them at the bottom of the drawer and never hand them in.
That makes a lot of sense. Albert, did you have something to add there?
Yeah, I mean, I probably don't have any really better information, but yeah, if you put them in the recycling stream, they will be recycled. If, as, say if it gets left somewhere, then not. I mean, I've heard figures of 50+% at this point overall of what should be coming back is being recycled. So
Excellent. That's great to hear. Okay, next question. Is there any data on the energy usage required for the recycling process? Specifically in terms of a per unit mass for the batteries themselves, the materials themselves, or the overall storage capacity?
yeah, I'm sorry that I don't have a direct answer to that right off the top of my head. Our models do give us those numbers, but I just don't know them off the top of my head. Essentially though, what you're looking at from a energy perspective, when you look up the slide I showed, actually just pull it up for myself. But essentially, recycling can be 50 to 80% of the cost or energy cost of basically making it from virgin materials. Yeah, it looks like about 70% for hydro and pyro, and you're looking at about 40% for direct recycling if we make that work.
Oh, that's higher than I expected. Thank you for that. Okay, next question again, talking about repurposing now. Are there any specific guidelines for where repurposed batteries go to usually in terms of other applications, or any thoughts, or are there any industries in particular that usually use repurposed batteries first off?
Well, maybe going first from our perspective and then the colleagues can weigh in, but the challenge has been actually getting your hands on end of first life batteries, right? Because if you look at it in outside of China and Europe, electrification at a larger scale really started in 2016. So if you look at an 8-year life or a 7-year life, then well, actually those batteries are only starting to just come back now. So we're at this sort of inflection point where we're going from a scarcity of end of first life batteries to actually having a bit. Most of the recycling that we're seeing at the moment actually, or repurposing, is with batteries coming from from the production line that didn't quite meet the battery grade and the automotive grade and are therefore going in other applications. But yeah, the other colleagues might have more to say.
I can confirm that. Yeah, basically, we have seen, I totally confirm what Stephen has said. Most of the supply for battery repurposing is coming from production line scraps. And those are basically what we can call battery supply. This is battery supply that is really kind of brand new battery supply, still in very good condition. And the typical uses for battery are for this battery are battery storage in the three main categories I explained before. So domestic residential applications. C&I is the most important category. So commercial industrial in the battery storage, and then grid scale like Stephen has explained just now.
Excellent. Thank you so much. Actually, a really good question just came in the chat here. Have we seen any OEM EV manufacturers that are offering a repurposing program? We know that there have been private scale interest in using old EV batteries for home storage systems. But has anybody seen anything like a commercial program?
Nissan had one for a while, but then they stopped with it when it was scaling up. They just sort of did it to learn. What we're seeing with a lot of the OEMs is they're a bit nervous about getting involved in it, because it's still very small scale. So I think they're sort of waiting for other people to trailblaze and for them then to potentially buy those parties, I guess. I think there are some OEMs on the heavy duty side who started sort of remanufacturing where, say, if you're getting a battery that's broke for whatever reason, they'll take it back. And then the new one they give you to meet their warranty obligations, that's often remanufactured or repurposed. And then thirdly, you've got some players on the passenger side who want to get in this game without doing the work. So what they're doing is rather than paying the cost to recycle, they're passing on the batteries either for free or for some sort of profit share to the parties doing the reintegration. Because I mean, the one thing we shouldn't forget is at the moment when you recycle, particularly LFP batteries, which have less precious materials, and there's quite a large gate fee, like with any waste that you try to get rid of, right? I mean, sorry to bring it back to buses and to trucks, which is what we know, where you've got sort of 400, 600 kilowatt hour batteries. I mean, I wouldn't be surprised to look at $16,000 plus logistics cost to get rid of a battery like that in some cases.
That actually makes a lot of sense. Again, with the materials and with the size that you're talking about there, and I think that honestly, I mean, vehicles and trucks and buses are what we'd be looking at mostly here. So that's perfect. So as a follow-up, if a fleet manager wanted to sell or recycle their batteries, how should they do that, or who would they be reaching out to? And again, that's open to anybody here.
I'm talking too much, so I'm going to let the colleagues do that first.
So in general, fleet operators, it depends if they have the direct relationship with OEM, with the auto manufacturers or not. So for example, OEMs are directly managing this type of operation related to disposal and repurposing EV and batteries at their end of life. So if the fleet operators or the business has direct relationship with the OEM, should contact the OEM for these projects, and then the OEM has partners most of the times that are handling this operation, like for example Zenobi or other similar businesses. And if the fleet operators prefer to go other routes, there are like marketplaces like ours that are collecting batteries from this type of businesses and finding buyers on the other side, or managing relationship for or finding a solution, the best solution we can for the end of life and repurposing of those batteries. So there are several opportunities on this side.
Thank you. Stephen, did you have anything else to add there as well?
I think the other bit is when you buy the vehicle, look at your contract, because I mean we've seen in Europe there's some legislation that says that the OEM has to take the battery back, but what the regulation is vague on is but they have to take them back, but can they send an invoice or not? So when you buy the vehicle, particularly if you buy large volumes, is trying to get those obligations set out very clearly, and who carries what bit of the cost, I think is would be my first bit of advice.
That makes sense. And as we're starting to see right to repair and some of these same questions also coming up now in American legislation and policy circles, I think that's something that I'll be paying attention to, and that might also inform this here in the States going forward as well. So another question, and I guess this is more directed at smaller size batteries. Is there any, has anybody heard anything or seen anything about smaller applications for repurposed batteries, say for hand tools, for power tools, yard equipment, etc., outside of either large scale stationary or vehicles?
So on this point, from our experience, the smaller the battery, the less valuable you can find on the repurposing side. So unfortunately, this has been our experience with small batteries. So we tried also to find solutions in the past for batteries that were coming from mild hybrid vehicles, particularly popular in Europe, like batteries that are around sizes of 1.5, 2 kilowatt hours for like smaller applications. But you can do some like pilots, you can do some tests that has been done in the past, but there is no significant opportunities from like an economic and financial standpoint in repurposing those type of batteries. Usually, and again, I come back on this point again. The category that is seeing the most important financial opportunity is commercial and industrial in terms of sizing on the battery storage side, and we are talking about anything between 300 kilowatt hour to 5 megawatt hours. So this type of I don't know if Stephen, you agree with me, but has been our experience.
Yeah. I think the I would agree with that. I think the small scale there's the problem that you got to forget is, I mean, if you look at the picture that I think Albert showed at the beginning, right? You show sort of the chemical picture, anode, cathode, electrolyte. But the thing that's you got to remember is there's this bit around it as well, which is the plastic, the insulation, and all the other stuff. And the smaller the battery, the bigger the plastic, the glues, and the other bit, the insulation is part of the weight. So, and how do you disassemble that, right? I don't know if anyone's here try to disassemble a hand tool battery. I mean, it's not something I recommend to try at home. It's difficult because they intentionally make it difficult from a safety perspective. So while if you go and have the opportunity to visit your local bus or truck depot, they can actually open the hood and you see the pack sitting there. You can electrically dismantle them and take a huge pack out, and each pack is, I don't know, 50 kilowatt hours. So it's a very different setup. The ratio of glue and plastic to battery is a lot better.
Absolutely. Spend time working on very, very large lead acid batteries and specifically recognizing that you do need to be able to have ease of access to get to them and also to swap out, say, bad cells quickly and efficiently is definitely something you want to have at a larger scale. And so economies of scale would work against you for the smaller scale ones there. So next question, are there any safety concerns if the batteries are repurposed or not damaged? I know we talked about this a little bit on the recycling side, but when the batteries are coming in to be repurposed, are there any safety considerations you're looking at?
Definitely. I mean, you got to check for visible signs of damage. Also, again, the data and everything helps. And then thirdly, also every battery we would repurpose, we electrically test, right, to try and see how does it behave under charging, discharging. Is there a swelling? Is there gassing? Are there other issues? So yeah, the health and safety aspect is absolutely critical. Also, in the containerized units that you put it in, you'll have fire detection, smoke detection, temperature detection, and various other safety measures. So yeah, it's absolutely critical.
Okay, next question. So as we are talking about, speaking of batteries being damaged, so what does happen when a battery comes in damaged or is damaged while it's in use?
Well, the ones that come in, and if it gets spotted that they are damaged, they will go towards recycling, right? And then there's a sort of separate triage system for how they get handled, because a safe, undischarged battery can be processed in a sort of standard process. For the damaged ones, say they've been in a fire or something like that, you got to dispose of them in a different way before you put them in the recycling process. You got to yeah let the fire end and then find a way to get the electricity out. Simplistically put.
Yeah, the other complexity there is the actual packaging and transportation requirements for a damaged, defective, or recalled battery. So that's the category that they consider basically high risk. And so at least in the US, the requirements are quite high to have a essentially completely fireproof box that you put around these, and they can be actually quite expensive and also pretty expensive to transport as well. Limited numbers on a truck, that kind of thing.
Yeah, and the other
They can
thing
actually
we found
transport.
that people often forget is it's not just the box and the truck, it's also the driver that needs to have a special license, which yeah, is very critical to check and monitor because it's hazardous. It's treated as hazardous waste, right? So as a customer contracting with said services, you've got to make sure that that's all in order because you're not just talking about corporate liability here, you're talking about personal director liability as well.
Absolutely. Thank you. Okay, so why do batteries typically fail? What are the usual, not just in terms of end of life discharge cycles, but say failures or failure modes or failure points for these batteries that we're talking about? Mhm.
But yeah, I can kind of go through that as sort of probably the most battery scientist on the call. So there's a few different mechanisms that really happen in a battery. One of the main one is essentially you start losing lithium into the films that form on the surfaces of your electrodes. Essentially, it means the lithium can't go back and forth anymore. So that's one of the main losses. That's why we have to re-lithiate for direct recycling, because you have to put more lithium back in. There's also those films create resistance, and so you won't be able to charge and discharge as fast. That also reduces your apparent capacity. And then if you do bad things to the battery, if you overheat them, those films grow a lot faster. If you charge really fast, you can get what's called lithium plating on the negative electrode side, and that basically just eats up lithium really fast. So if you charge faster than you're supposed to, that will cause really rapid failure. Also, the materials do degrade to some extent. You can get cracking and other things in the actual cathode material that'll eventually cause you to lose electrode that can't be used anymore, essentially.
Okay, and this is the last question that I have so far. Um, can you share any real-world applications for reusing batteries that we're currently seeing, or where are we seeing the most popular ones? Stephen, you touched a little bit on this already, but anybody else who's got any information or any experiences that have been particularly useful or advantageous?
I didn't fully catch that.
Uh, Real-world applications for reusing the batteries that we've been talking about here.
I think the any place that use a diesel generator is a good place to start in terms of looking for applications. Because well, reducing diesel consumption by having a sort of a battery peaker in the middle is great. Construction, film, conferences, putting them back into places where you need charging or you have grid constraints are all things that we have done. Short to ship power. We've even powered a container ship at one point with some old Second Life EV bus batteries. So yeah.
Yeah, and as we said before, yeah, any kind of off-grid power generator, or that could be based on reused battery or battery storage applications, again, that are useful to either stabilize the grid, frequency regulation, ancillary services, and if we are coming down to smaller applications in the CNI, also help the companies to reduce their energy cost. Yeah, those are applications I explained before, and those are like the most frequent use cases for repurposed batteries.
Great, thank you. Let's see. Okay, there's another good safety related question. Is the International Fire Code up to date on the requirements for storing the batteries in the types of applications that we're talking about? Just because, again, we are talking about very, very difficult firefighting sometimes here.
Want to have a better answer to that. I don't actually know where they are on updating those regulations. I know there's a lot of work in progress at all the standards organizations to try to address battery safety, battery, reuse, all these kinds of things. The standards are continuously being updated right now. There's a lot of work in progress on that front. I can tell you a bit about what people are thinking about for firefighting. And there's different approaches to how that's done. So one thing is, essentially a lot of the firefighting now is massive quantities of water, which can be effective, although you have to worry about relighting the batteries. Um, there are folks that are thinking about, which from a battery person perspective, like it's crazy, spearing the battery with basically a water pipe. So you can inject water into the battery pack to fight the fire directly. It may be workable. It may be reasonably safe. It sounds scary as could be, but people are developing those as technical solutions. There's also people who try to fight these things with sand and the like, which is effective, but can you really dump enough sand in an efficient way? So there are some decent options. I mean, water is actually reasonably effective at putting them out. You just have to watch for relighting, and it does take time because, as I said, they have all the things. Yeah, I mean, the other part of that is, sprinklers are actually very helpful, and they've shown that, particularly in smaller battery fires, having sprinklers can be a life-saving measure. So I think a lot of that's probably going to be incorporated in the new codes, but I am not an expert and I won't speak to the fire
From
codes.
what we've seen, it's in many cases it's a very local thing, fire code, right? So you have the national level, but involving your local fire department and who sets local guidelines and stipulations as early on in a project is important. I think the other thing we shouldn't forget about is these things catch fire a lot less frequently than a diesel engine or a petrol car by quite a large magnitude. So could put things in perspective as well. But then obviously you need to be ready for the events as and when.
Absolutely. Thank you. Are there any other questions? And Heather, anything else before we say goodbye to everybody?
No, just wanted to thank everyone for joining in and listening today. Thank you to our speakers for speaking, and thank you, Ted, for moderating. We really appreciate it.
Absolutely. Thank you so much. This has been a great discussion again. Everybody who participated, thank you so much. I've learned a lot that I'll be able to take back and that I'll be keeping my eye on as well.
And with that, I'd like to also thank you, Ted, for great moderating, excellent presentation to everyone, coming away with a lot of information here. If anyone needs to contact any of our speakers and you didn't get their contact information, please feel free to send an email to Heather or myself, and we will make sure it gets to the correct person. Thank you again to our sponsors. And with that, that will conclude our webinar. Have a great rest of your day. Thank you, everyone.
Bye, everyone.